What's going on, everybody? This video we're going to look at using derivatives in curve sketching. So basically what we're doing in this video is we're graphing polynomials using calculus. Okay, so let's go ahead and get started. We've got several examples. The first three examples we're not graphing, we're just finding like increasing, decreasing, and then in the next example relative max and min, and then the third example, concavity and inflection points, and then we have a couple of problems where we're going to actually graph using all that stuff. All right, so the critical numbers for a function f are the number c in the domain of f. That's important there. Okay, c has to be in the domain of the original function for which f prime of c equals 0 or f prime of c does not exist. So basically what that means, to find a critical number, you take the derivative, set it equal to 0, and solve for x. And then also the critical numbers are where the first derivative is undefined, but it has to be defined in the original function. Okay, and this part right here, the f prime of c does not exist, that's not going to really apply to this section. This will be more in the video after this one when we get into rational functions and stuff. Increasing and decreasing. If f prime of x is positive for each x in the interval, f is increasing on the interval. And if f prime of x is negative, less than 0 for each x in the interval, f is decreasing on the interval. And if f prime of x is equal to 0 for each x in the interval, then f is constant on the interval. So that might sound like it's, oh, I don't really know what to do or how to do that. It's really not bad, and you're going to see that when we work this first example. So let's look at the first example. It pertains to this right here. All right. So it says find those values of x for which the function f of x equals, so f of x is equal to x cubed minus 3x squared is increasing, and those values for which it is decreasing. All right, so the first thing we need to do, and that's all we're finding in this example, is increasing and decreasing. So the first thing we need to do is take the derivative. We're going to find the critical numbers. So that's 3x squared minus 6x. All right. And then we take the first derivative, 3x squared minus 6x, and set it equal to 0 and solve for x. So let's factor out a 3x. And so that's going to leave me with x minus 2 equal 0. And so I get 3x equals 0 or x minus 2 equals 0. And so x equals 0 or x equal 2. Okay, so these are our critical numbers, 0 and 2. So now I want to determine where this thing is increasing and where it's decreasing. So what I'm going to do is I'm going to take the critical numbers and I'm going to plot them on a number line. And in this case, I've got two critical numbers, so you can see it divides the number line into 3 regions. And what I'm going to do is I'm going to pick a number from each region. Okay? It makes no difference what numbers you choose as long as you choose numbers from each of the regions. Like for instance, I chose x equal 3 there. If I wanted to choose x equal 5 million, I could. But why would you do that? Pick something that's easy. Okay? Next, what does it say? It says I need to determine if the first derivative is positive, negative, or 0. So let's look. So I want to do f prime of negative 1. I'm going to evaluate each one of these values that I chose in the first derivative. Now look, I can take the negative 1 and I can plug it in for x here and evaluate it. Now, would you agree that this is the same thing as this. It's just this one's factored, right? But it's still the same thing. So what I'm going to do is I'm going to take the -1 and I'm going to plug it into here because it's easier. If you wanted to plug it into this one, that's fine. Okay? So let's plug the -1 in. So if I plug the -1 in, I get 3 times -1 is -3. And then -1 minus 2 is -3. So look at this. I've got a negative. When I plug the -1 in, I've got a negative times a negative, which is positive. That's all I care about. I don't care what the exact number is. All I want to know, is it positive or is it negative? And I can see when I plug in the -1, I get a positive. And so that means it's increasing. And then if I do the same thing, f prime of 1, well, that's positive, because 3 times 1 is positive 3. And then 1 minus 2 is a negative, so I've got a positive times a negative, which is negative, so that's less than 0, so that's decreasing. And then if I do f prime of 3, so I plug the 3 in, that's positive here, positive here. Positive times a positive is positive, and so that means it's increasing. So I have this thing is decreasing from 0 to 2, and it is increasing from -infinity to 0 and from 2 to infinity. And so that's what they were wanting us to find. Okay, so that's not bad. Just remember, all you care about when you evaluate that first derivative is it positive or negative. And look, if you want to plug the numbers into here or here and get the exact number that it is, that's fine. But all you care about is it positive or negative. Okay? All right, let's look at this. We've got relative maximum and minimum. Let C be a number in the domain of a function f, then f of c is a relative maximum for f if AB contains c such that f of x is less than or equal to f of c for all x in AB, and f of c is a relative minimum for f if AB contains c such that f of x is greater than or equal to c for all x in AB. So basically what happens is you have an interval here, AB, and you look at all the values between A and B, and if C is in here somewhere and it's larger than all the other values, then it's a relative maximum. If you have C and that value f of c is less than all the other values in here, then it's a relative minimum. That's what that's saying. And so now we have the first derivative test. This is how we can test to see if there's a relative max or min. It says c is a critical number, f is differentiable on AB except possibly at c, and c is the only critical number of f in AB. Then f of c is a relative maximum of f if f prime of x is positive in AC and f prime is negative in CB. And f of c is a relative minimum of f if f prime is negative in AC and f prime is positive in CB. So let me just show you what that looks like. So you've got A, you've got B, and you're just looking in this interval right here, and let's say you have some number in here, C. So what it's saying is if the derivative, let's just look at the relative maximum, relative minimum would be similar. So if f prime is positive in AC, so in AC f prime is positive, meaning it's increasing from A to C, and then and f prime is negative in CB, so from CB in this part it's negative, the derivative is, which means it's decreasing, you can see you have a relative maximum. And then it's similar for this. In AC it would be decreasing, CB it would be increasing. You would have a relative minimum. Okay. All right. So let's look at this. Find this example. Find any maximum points and minimum points of the graph of the function. So we have y equals 3x to the 5th minus 5x cubed. So we want to find any relative maximum or minimum points. And look, it's really easy. We've really done most of the work already, or we already worked most of this problem up here in this part. So basically what we're going to do to find relative max and min, we're going to determine where it's increasing and decreasing. Okay, so let's do that. So we remember how to do that from the first example. So I have y prime is equal to 15x to the 4th minus 15x squared. So 15x to the 4th minus 15x squared equals 0. So I'm going to factor out a 15x squared, and that's going to leave me with x squared minus 1 equals 0. So I get x squared equals 0, or x squared minus 1 equals 0. So x equals 0. Here x squared equals 1. X equals plus or minus the square root of 1, and the square root of 1 is 1. Now notice I didn't bring the 15 down here. I could have 15, and then all you're going to do is divide both sides by 15, so you'll just end up with x squared equals 0 anyway. Okay, and so x is equal to 0. All right, so I've got my critical numbers, 0 and plus or minus 1. So let's go ahead and plot those on a number line. All right, and we're going to choose a number from each region. And like I said, this you can choose any numbers you want. And then what we're going to do is we're going to plug each of these in to the derivative. And once again, you can plug it into here, or you can plug it into this one down here. It doesn't matter. Okay. So I've got y prime of negative 2. Okay, y prime of negative 2. So I need to plug the negative 2 in. Now look, let's use a little common sense here. Do you realize any of these numbers that I plug in, that this one out here is going to always be positive? Okay, that term's going to always be positive. So I just need to look in here. All right, so what is negative 2 squared minus 1? That's positive, isn't it? Okay, so that would be 4 minus 1. That's positive times a positive is positive, so that's positive. So that means it's increasing. And now let's do y prime of negative 1/2. So if I plug the negative 1/2 into here, that's going to be 1/4. 1/4 minus 1 is negative. A negative times a positive is negative. And so this is decreasing. And then same thing here when I do y prime of 1/2. Well, that's negative times a positive is negative. So that's decreasing. And then when I plug the 2 in, that's going to be a positive times a positive. So y prime of 2, positive times a positive is positive. So that's increasing. So far we haven't done anything different from what we've done in the first example of determining increasing and decreasing. But all they're asking us for now is relative max and min points. Okay? And look, if you do the number line and you draw your arrows like this, look at this. There's your relative maximum, and there's your relative minimum. And there's nothing here. They're both decreasing here, so there's no relative max or min right there. But there's your relative maximum. There's your relative minimum. So I have a relative minimum at the point where x is equal to 1. All right, now look. I need what? I need a point. I've got the x coordinate. I need the y coordinate. This is where students mess up all the time. So to get the y coordinate, where do I plug the 1 into? I have to plug it back into the original. Students all the time plug it back into the derivative. You don't do that. You're looking for x, y. Where is y? Y is right here. So that's where you plug it into. So let's just show it. So that's 3 times 1 to the 5th minus 5 times 1 cubed, which that is -2. So I have a relative minimum at 1, -2. And then I have a relative maximum at -1. At -1. And so y of -1, I need my y coordinate. So that's going to be 3 times -1 to the 5th minus 5 times -1 cubed. So that's -3 plus 5 is 2. So here's my relative maximum and minimum point. All right. All right, so let's look at this. We have the second derivative test. So there's another way that we can determine relative max and min. And honestly, to tell you the truth, I don't really use the second derivative test to determine maximum and minimum because I can do it right here. But there is a second derivative test for maximum and minimum. So what does it say? If f prime of a is equal to 0 and f double prime is negative, then f of x has a relative maximum at x equal a. And if f prime of a is equal to 0 and f double prime of a is positive, then f of x has a relative minimum at x equals 0. So the other way that we can determine if it's a maximum or minimum is we can plug the critical numbers in. You see that? We can plug these critical numbers in to the second derivative. If it's negative, it's a relative maximum. If it's positive, it's a relative minimum. And I guess I'll just show you that real quick. So let me just kind of erase this right here, and we'll do the work here. We'll do it in a little bit different color. So if we find the second derivative is, what is that? Let's see, that's going to be what? 60x cubed minus 30x. So if I do y double prime of -1, that's going to be, what is that? -60 plus 30. See that? -60 plus 30, which is negative. That's less than 0. So you see the second derivative gave me negative, and there is a relative minimum. And then y double prime of 1, let's erase that equal. Y double prime of 1, that's 60 minus 30 is positive. And so for the second derivative test, since the second derivative is positive, that would give me my relative minimum. And then y double prime of 0, well, if I plug the 0 in, that is actually equal to 0. So what happens when the second derivative, you're using the second derivative test and you get 0 as an answer? Well, that means the test is inconclusive and you've got to go back to the first derivative test. So, like I said, I always just use the first derivative test. I can't remember whenever I have used the second derivative test. Okay, I just used the first derivative. All right, so that's maximum and minimum. All right, so now let's look at tests for concavity. So let f be a function with f prime and f double prime existing at all points on AB. F is concave upward on AB if f double prime is positive for all x in AB. and f is concave downward on AB if f double prime of x is negative for all x in AB. All right, so that's how we determine concavity. Is it concave up, concave down? And then points of inflection, the point at which the curve changes from concave up to concave down, or from concave down to concave up, are known as points of inflection. So basically what that means, your points of inflection, wherever it changes concavity, you're going to have an inflection point there. So let's look at this example. So in this example, all they're asking us to do is find concavity. And then after this example, we'll have a couple of problems, I think 3 problems where we actually graph and we have to find all of this stuff. So determine the concavity and find any points of inflection of the function. So we've got y equals x cubed minus 3x. So we need the second derivative. So y prime is 3x squared minus 3. Y double prime is equal to 6x. Okay, there's a loud truck driving by right now. All right, so we take the second derivative and we set it equal to 0 and we solve for x. So we get x equals 0. And then we plot that on the number line, 0, and it breaks it up into 2 regions. And so I pick a number from each region. Okay, so you can see this is similar. It's just like what we're doing when we were determining where is it increasing and decreasing. The only difference is we're doing it with the second derivative instead of the first derivative. We're basically doing the same thing. So I've got y double prime of -1. So I plug the -1 into the second derivative, and that's going to give me a negative. That's less than 0, so that means it's concave down. And then I do y double prime of +1, so 6 times 1 is positive, so that means this is positive. So here it's concave upward. And so concave downward from -infinity to 0, and concave upward from 0 to infinity. So there's my concavity. And then it wants us to find points of inflection. So that's where it changes concavity. You can see it changes concavity at 0. So points of inflection. And that's at 0. And then once again, I need a point. I need a point. So I need the y coordinate. So where do I plug this 0 in? You plug it back into the original. So that's like y of 0 is 0 cubed minus 3 times 0, which is 0. And so there's my point of inflection. Okay. All right. So hopefully all that made sense. Okay. Now, these next examples sketch the graph. That's what they're wanting us to do, is sketch the graph. And what we're doing, basically what you do to sketch a graph, all these examples that we just worked, that's what you got to find. You got to find your critical numbers, where it's increasing and decreasing, relative max min, and concavity and inflection points. You find all of that and you use that information to sketch the graphs. Okay, so the first 3 examples were just, okay, here's how you find where it's increasing, decreasing, and here's how you find the critical numbers. And then we had another example, here's how you determine relative max and min. And then the last example we just worked, how do you determine concavity and inflection points? So we just went through each little part. Now we got to put all of it together to graph. All right, so sketch this graph. So I've got y prime is 6 minus 2x. Okay, so we take the derivative, set it equal to 0, and I end up with x equal 3. Move the 2 over and then divide by 2. All right. And so now what we want to do is plot that number on the number line, choose a value from each region, okay, and then I've got y prime of 2. Whoop, I don't really need equal, but y prime of 2. When I plug the 2 into here, that's going to be 6 minus 4 is positive, so that's greater than 0, so that's increasing. And then y prime of 4, 6 minus 8 is negative, less than 0, so that means it's decreasing. So I've got decreasing from 3 to infinity and increasing from negative infinity to 3. And what I like to do is go ahead and circle your increasing, decreasing, relative max, min, concavity, and inflection points. Circle each of those so it's easy for you to go back and find them, because that's the information you're going to be using to sketch these graphs. Okay? So now we can see we have a relative max at 3. See? Look at this. There's your relative max at 3. And so I have a relative max at 3, and then I plug it into here, right? So 6 times 3, so look at this. Y of 3 is 6 times 3 minus 3 squared, so that's 18 minus 9 is 9. So I have a relative max at 39. Okay, so we're basically just going through and finding all the stuff we need. Okay, so I've got increasing, decreasing, relative max, min. Now I've got to determine concavity, and so I need the second derivative for that. There's the first derivative. The second derivative is just -2. Okay. Well, look at this. We don't have an x in there. We can't set that equal to 0 and solve for anything. So what do we do now? Well, it's basically saying the second derivative is negative, no matter what you plug in. You see that? It doesn't matter what number we plug in here. We can evaluate y double prime at any number we want, and we're always going to get -2 as an answer. It's always going to be negative. So that means this thing, since the second derivative is always negative, that means it's concave downward over the entire number line from negative infinity to positive infinity, and points of inflection. Well, what would be the points of inflection? Well, if it's always concave downward, it never changes concavity, so there's points of inflection, there's none. So now let's graph this thing using the information we have. All right, so I got 1, 2, 3, 1, 2, 3. And so really the only point we have to plot is the point 3, 9. So 3, and then I'm going to go up to 9, and I'm just going to estimate it about right there. Okay, we'll call this 9 right here. All right, so let's look at it. Well, it's concave down everywhere, and let's see, from negative infinity to 3. So over the x values, as I'm coming in from negative infinity to 3, it's increasing. You see that? It's increasing. So that means this thing is coming in like this. And then once it gets to 3, from 3 to infinity, it starts decreasing. And I know that doesn't look very pretty, but it's good enough for this video, right? And so there you have it. This is actually the point 3 negative, I'm sorry, not 3 negative 9, it's 3, 9. There's your point. And look, is this thing concave down? Yes, it's concave down everywhere. And, you know, on this one, looking at that, we know 6x minus x squared, we know that's a parabola. There's a negative in front of the squared term, so we know it's a parabola that opens downward. There it is. There's your parabola that opens downward. Now, I'll say on this problem, we didn't really need calculus to graph this thing. Okay? I mean, we know how to graph a parabola by finding the vertex, right? Find the vertex, x and y intercepts, and then we can sketch the graph. Okay? But, you know, it is what it is. There, you know, we use calculus to do it. And we actually found the vertex. There's our maximum point. And you know a parabola that opens downward, there is a maximum. All right, let's look at the next example. All right, so let's graph this one. So I've got y prime is equal to 6x squared plus 6x minus 12. And so 6x squared plus 6x minus 12 equals 0. I'm going to divide everything by 6. X squared plus x minus 2 equals 0. So x plus 2 times x minus 1 equals 0. X equal negative 2 or x equal 1. All right, so there's my critical numbers. And so I'm going to plot those on the number line. So I've got negative 2, I've got 1. So I've got x equal negative 3, x equal, and we'll do 0, and x equal 2. And so I've got y prime of negative 3. Now, what I'm going to do, I'm just going to plug it into this one because all I care about is it positive or is it negative. That's the only thing that matters. So if I plug the negative 3 in, that's a negative. That's a negative. Negative times negative is positive, so it's increasing. And then y prime of 0, so that's going to be positive, negative, that's negative, so that's decreasing. And then y prime of 2, that's going to be positive, positive, positive times a positive is positive, so that's increasing. So we've got decreasing from negative 2 to 1, and we've got increasing from negative infinity to negative 2 and 1 to infinity. All right. And so there's my increasing and decreasing. And you can see here I have a relative max and I have a relative minimum. So my relative min is at 1. And so then I've got to plug 1 into here. Okay. So that's going to be 2 plus 3 minus 12 is negative 7. So that's the point 1, negative 7. And then I have a relative max at negative 2. And then I need the y coordinate. So I'm plugging negative 2 in for x. So that's negative 8. So that's going to be negative 16. And that's going to be plus 12. And then plug it in negative 2, so plus 24. And so that's going to be 20 is my relative max. Okay. And hopefully I didn't mess up putting that in. I don't think I did. But there's my relative max and min. As long as I punched everything in the calculator right. All right, so now what do we need? Well, now we need the second derivative. So the second derivative, I'm going to take the derivative of y prime. So that's going to be 12x plus 6, right? Yep. And so 12x plus 6 equals 0. So x is, what is that, negative 1/2. Okay. All right, so let's go ahead and put that on the number line. So negative 1/2. And so I'm going to choose x equal negative 1, x equal 0. So this, I've got to plug into the second derivative. So the second derivative evaluated at -1, I'm plugging it into here. So that's a -12 plus 6 is negative. So that's less than 0. So that means it's concave down. And then I do y double prime of 0. That's 0 plus 6 is positive. And so that's concave up. So concave, I'm going to abbreviate this. Concave down from -infinity to -1/2, and concave up from -1/2 to infinity. And so inflection point, it changes concavity at -1/2, and then we take the -1/2, we plug it back into the original, and once we do that, we get 13/2 is the inflection point. So let's circle all that. And so now we're ready to graph this thing. All right, so let's see. I've got 1, 2, 1, 2. And so let's see, I'm going to plot the point 1, -7, which we'll say that's about right there. And then -220, we'll call that up here somewhere. And then -1/2, 13/2, -1/2. Let's see, 13/2, that is 6.5. So we'll say that's probably about maybe right in there, something like that. All right, so let's see what this is doing. So this thing from -infinity, I'm coming in from the going left to right, -infinity to -2, it's increasing. All right. And also all the way up to -1/2, coming in from -infinity, it's concave down. So that tells me the graph's going to look like this. And so it's coming in here like this. Okay. And then, let's see, from -infinity, from -infinity to -2, it's increasing. And then once it hits -2, you see the -2 to 1, it's decreasing. So it is coming down like this. Okay, like this. And I'm drawing it through 0, 0 because I know it's going to go through that point, because if I plug 0 in for x, I get 0 for y. So I could maybe draw that a little better. Something like that. It's decreasing. But then, look, when it gets to 1, from 1 to infinity, it's increasing. Okay? And so it's going like this. And you can see that from -1/2, see the -1/2 here to infinity, -1/2 to infinity, that's when it's concave up. So you can see concave down, and then right here it switches to concave up at our inflection point, -1/2, 13/2. And you know, you can label the points here if you want. Your teacher may want you to. That's fine. I'm not going to write them in there for the video, but you know, you can go ahead and write. Well, let me go ahead and do it. 1, -7, -2. No, that's not -220. -220, and then this is -1/2. That's a -1/2. -1/2, 13/2. And so there's that graph. You see how easy calculus makes this to graph these things. All right. So now the last example. So let's see what we have here. Same thing. Y prime, that's 5x to the 4th minus, what is that, 20x cubed. And so 5x to the 4th minus 20x cubed equals 0. So I'm going to factor out a 5x cubed, and that's going to leave me with x minus 4 equals 0. And so I get x cubed equals 0. I could bring the 5 down, but I'm going to end up dividing by 5, and that'll just leave me with x cubed equals 0. Or x minus 4 equals 0. So x equals 0 or x equal... Whoop. Did you see that? My battery's going dead. Let me plug this in. All right, we're charging now. I get x equal 4. All right. So there's my critical numbers. All right, so let's see. Let's draw the number line. So I've got 0, I've got 4. So I'm going to choose x equal -1, x equal 1, and x equal 5. So I've got y prime of -1. So I'm going to plug that into here. So if I plug the -1 into here, this out here is negative, this here is negative, negative times a negative is positive, so that thing is increasing. And then if I do y prime of 1, let's see, what's y prime of 1? That's going to be a positive, a negative, so that's negative, so that's decreasing. And then y prime of 5, let's see, that's positive, positive, so that's positive, so that is increasing. So we have decreasing from 0 to 4, increasing from, let's see, -infinity to 0, and 4 to infinity. And you can see we've got a relative max, we've got a relative min. So relative minimum at 4. All right, and then we have to plug 4 into here. Okay, we got to plug 4 into here. So what do we get when we plug 4 into that? I'm sorry, I said here, I meant here. We got to plug 4 back into the original. And when we do that, we actually get, let me leave myself a little more room, we get -256. That's a big number. And then we have a relative max at 0. And so the relative max is at 0, 0. So there's my increasing, decreasing relative max min. Excuse me. All right, so now let's look at concavity. So I need the second derivative. So the second derivative, that's going to be 20x cubed minus 60x squared. Yeah. And so 20x cubed minus 60x squared equals 0. Factor out a 20x squared. That's going to leave me with x minus 3 equals 0. So x squared equals 0, or x minus 3 equals 0, x equal 3. Or x equal 0. So let's plot that on the number line. We got 0, we got 3. So x equal -1, x equal 1, and x equal 4. So I've got to do y double prime of -1. So once again, make it easy on yourself. This out here, no matter what you plug in for x, that's always positive. So let's see what we get inside these parentheses here. So -1 minus 3 is negative. Negative times a positive is negative. So that's concave down. And then y double prime of 1. So that's positive, negative. That's less than 0. So it's concave down. And then y double prime of 4. That's positive, positive. So that's positive. So that's concave upward. Okay, so we've got concave down. It's concave down from -infinity to 3, and it's concave up from 3 to infinity. Okay? And then we've got points. I'm going to abbreviate that to inflection point at 3. See, it changes concavity at 3. It does not change concavity at 0, but it does at 3. So there's an inflection point at 3. And then we've got to take the 3, plug it back into the original. And when we do that, we get negative 162. And so let me circle all of this, so because that's the information we're going to use to graph this thing. All right, so let's see what we've got here. All right, so I've got a relative max at 0, 0. And then we've got the point 4. So 1, 2, 3, 4. And then negative 256. We'll say that's about right there. This isn't going to look to scale at all, is it? And then 3, negative 162. So that's going to be a little closer to this point right here. We'll call it right there. Okay. So now let's look at this. From, where is it? From negative infinity to 0, it's increasing from 0. So it's increasing to here. And then it starts decreasing when it hits 0. And then when it hits 4, it starts increasing again. Okay. But keep in mind that it's concave down all the way till we get to 3 here. So this thing's going to look something like this. It's going to flatten out a little bit here. Like this, and it's decreasing. Probably maybe a little flatter there. But see, it's decreasing all the way to this point until we get to 4. See, it's decreasing from 0 to 4. It's increasing from negative infinity to 0. It's concave down all the way to here, to where we get to 3. And then once we hit 4, it starts increasing again. And so it's going to come up like this. And that's your graph. This is the point 0, 0. This is the point 4, negative 256. And this is the point 3, negative 162. Okay. So that is the graph. Okay. And that's also the last example. So I hope this helped. Just remember, whenever you're graphing these things, critical numbers, increasing, decreasing, relative max min, concavity, inflection points, and then use all that information to sketch the graph. And that's the end of the video. I hope it helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all in the next one. Later.